Hello everyone, welcome back. I am Mr. Cobalt, and in this video I'm going to talk about Charles' law, the relationship between volume and temperature. So let's go back to our equation for pressure and related to force and area. So pressure is equal to force over area. And let's think about what's going on with the gas in terms of volume and temperature, and how that might relate to pressure as well. Even though we're not going to be dealing with pressure in the law itself, but I think it'll help think about what's going on. So remember what I said about temperature. Temperature is related to or proportional to the speed of particles, or particle speed, right? So that means if you increase the temperature, you're increasing the speed of the particles, and vice versa. If the particle of speed increases, then the temperature is going to increase as well. If you decrease temperature, then you're going to decrease the speed of the particles. But then think about what happens when you increase or decrease the speed of the particles if they're in a container, and think about how that relates to pressure. So if you increase the speed of the particles, then the particles are going to hit up against the wall of the container harder, and they're going to give more pressure, give more force, I mean. But then the force is also going to equate to pressure as well. So the faster the molecules are moving, the more force you're going to be hitting the sides of the container, and the more pressure you're going to have. Well, what happens to the volume if the pressure goes up? So temperature goes up, force of the molecules hitting the sides of the container goes up, and then the pressure goes up. What's going to happen to the volume, right? Think about a balloon, right? You have a flexible surface, a flexible container. If the pressure goes up, what happens to the volume? The volume increases, right? Now, what happens if you decrease the temperature, right? So here we're saying temperature increases. What happens to the force? The force is going to go up. The force that the particles are pushing on goes up. If that goes up, what happens to the pressure? That also goes up. So if the pressure goes up and you have a flexible container, what's going to happen to the volume of the container? It's going to increase because the pressure is pushing out more. So if temperature goes up, then pressure is going to go up, and then therefore volume is going to increase. So here you have a direct relationship between temperature and volume. And then we can understand that from understanding what's going on at the particle level, at the molecular level. So if I write this down as a direct relationship, then this means that if T is directly, T is going to be temperature is directly proportional to volume, right? So again, if I multiply this by some sort of constant, I can get an equality, right? So there's some constant I can multiply by that's going to make this equal. So volume times the constant K will make this an equality. I don't know what K is, but whatever it is, we can assume that there is some sort of constant. So if I want K by itself, I would divide by V, the volume. Volume will cancel out, and now I get temperature over volume is equal to some constant K. Okay, you with me so far? So now I have T over V is equal to K. Now I can kind of see the direct relationship. Now what happens if I double the temperature? If I increase the temperature by doubling it, what happens to K? If nothing happens with volume, then K will be doubled as well, right? But K is supposed to be constant. It's supposed to stay the same. So if I want K to stay the same instead of doubling, then if I double the temperature, I have to double the volume too, because watch what happens when I double this. So 2's cancel out, and it's back to the same thing. So here you can see the direct relationship. Whatever I do to the temperature, I have to do the same thing to the volume. If I half the temperature, if I cut the temperature in half, then I have to cut the volume in half. If I triple the temperature, then I have to triple the volume, and vice versa. So this says that if I make any change to the temperature, then the volume has to change in the same way in order to keep K the same. So I can start with some temperature 1 and some volume 1, and that's going to equal K. If I make a change in the temperature, right, if I change the temperature to T2, then I have to also, the volume has to change as well in order to keep K the same. So I'm going to end up changing the volume to some volume V2. And that is going to be equal to K as well. And if you remember from the logic lesson or from before when we were talking about Boyle's law, if you have two things that are equal to the same thing, those two things have to be equal. And so if we set them equal, we would have T1 over V1 equals T2 over V2. And this is Charles's law. So if everything else is kept the same, so if the amount of gas is not changed, and if the pressure stays the same, right? Notice that there's no pressure here. So pressure has to stay the same, and the amount of gas has to stay the same in order for this to hold. So the only thing that changes is temperature and volume. And that's Charles's law. So I hope you can see where Charles's law comes from based upon our understanding of what's going on at the molecular level. I hope this was interesting and helpful. If you like this video, like it, share with your friends, subscribe to the channel, make a comment in the comment section. Let me know what you think and what you would like to know more about. And make sure you hit the notification bell to get notified of any new videos I have. Thanks for joining me, and I'll see you next time.